Hello, my statics friends. In our last video, we introduced the concept of equivalence and defined the two types of equivalence that are commonly encountered in a statics problem. The first one was the single force resultant, and we showed you some examples in that one. In today's video, we're going to talk about the second of those two, which is the equivalent force couple system. And again, I'll have an example for that as well. So without further ado, let's get started. So when we talked about equivalence in the last video, we kind of described it as a system of two different systems that were, well, equivalent. In the first picture that I show here, this is what we call our before system, and this is the same graphic we showed last time. Okay, I have an object with, say, at a point A force and a moment. At a point B, I just have a force, and then at some point D, I have a moment being applied concentrated. Okay, and then for reference, we have a point C that's somewhere on the object. Okay. In the last one, when we did single force resultants, there was information that we didn't know. For one, we didn't know that the location of C exactly, but we were able to write equations and to solve for it. In this one, now we do know the location. Okay, meaning that if I have a coordinate system set up with my origin O here at 0, 0, 0, then I can define a vector that goes from this 0 to the point that's being that we're interested in. And usually in a problem it will say, at point B, what is the equivalent force couple? Or, what are the support reactions at point C? Whatever the case may be, this is a point that you can define on the system geometry. And by that we mean we can write a vector that C has coordinates xc, yc, zc as its potential location, but that they are known. That's the biggest thing to take away from all of this. Okay, the equivalent system then, for after, looks exactly the same as the last time, with one exception. At point C, we have an equivalent force vector, and at point C, we also have an equivalent moment vector, except this time, the value of that resultant moment may or may not be equal to 0. It can be 0, okay, in which case that system is the same as the single equivalent force, but more than likely the moment is not 0 at the point that we're specifying, in which case now we have a difference. Okay, so to kind of compare, what we have here is that for both cases, FR is known. Okay, I can find FR by looking at what I did on the before system. Okay, the vector R from O to C, that's the vector that was coming up to here and pointing at that point, is a known value, meaning that it has the value of xc, yc, and zc if I use my calculus vector notation. All right, and then finally, the moment this time is unknown. Okay, it may be 0, but we don't know for sure. We'll have to do the calculations to prove it. Whereas before, the moment on this picture, remember we drew it with a dotted arrow and meant that it was a 0 value always at that point. Okay, and that was the definition of the single force resultant. All right, so let's take one and give it a shot and kind of write out the system. We're going to do the long method on this and kind of write the whole thing out step by step so you can see how we set this up. It'll be very similar to what we did in the last video. So I have an object this time. Now I'm doing a two-dimensional object, but this works for 3 dimensions. Okay, and so what we have is I have a fixed kind of cantilever system on this that has a moment at A, an upward reaction AY, and a leftward reaction AX. Okay, and so this, again, this is two-dimensional, so my moment is actually acting about the z-axis. I've defined x positive to the right, y positive up, and making, if I follow my right-hand rule, that z then, remember, thumb x, forefinger y, middle finger points out of the page, that's your z direction on that. Okay, we have a series of points to define the object. I have point A, which is at the wall. I have point B, which is 2 meters along the x-axis from A. I have a point C, which is now 0.75 meters above B and has a force of 200 newtons that we will call P1. This is the magnitude of the force, but we do know the direction, that it follows a line that is a unit of 3 over 4 up. Okay, so this is one of those perfect proportions that we talked about. Okay, meaning that this is a 3, 4, 5 triangle defines the slope, and with that I can get the angle, I can write a unit vector, whatever the case may be, to define that force. But it is a force that is both in the x direction and in the y direction both. Okay, and then D is the corner, that is 5 meters from A, and then E is 1 meter below D, and at that point I have a concentrated moment that I'm going to call ME that has a magnitude of 300 Newton meters. Now, noting the direction of this is counterclockwise. Our sign convention is that counterclockwise moments are positive, so we'll write that as a positive 300 Newton meter acting in the direction shown. All right, now, that's kind of the way that a scalar problem is presented to you. What I'm going to do is I'm going to turn everything back to vectors. We're going to write all the forces as vectors, we're going to write all the moments as vectors, and then we'll set up our equations in exactly the same fashion that we did last time in the last video. Okay, what we want to find then is the equivalent force couple at A. What's the equivalent of all of this system happening at that point here? And it turns out that this is actually the first step that we'll introduce in the next chapter, in which we start applying equilibrium and using equivalence to now give us unknown values such as support reactions. Okay, and this is the exact problem that you'll see when we start doing that. So, all right, so let's go through. So that was our before picture. Let's take a look at our after picture. And I just realized I didn't write after on this. So here's after. Okay, and so remember, just like before, the whole thing about after is that we draw it to the system that we're being asked to find. So this is an equivalent force coupled system. So we have our object again. I didn't put the dimensions on this time, but they're the same. I have the same support reactions because for these two pictures to be equivalent to each other, they have to have the same support reactions. Okay, so, but I don't know their values, so I'll just write them on there. They're in the same directions. My coordinate system is exactly the same. And then at this point, we know that we have a force resultant vector that we're going to call as FR, and I'm going to put an A superscript to tell me the location of that force resultant. And then we have a moment being applied that we're going to call MR as a vector, and again with an A superscript to indicate that that's at my point A. Point A is right there. All right? So that's what we do. So again, the moment may or may not be zero. We'll find out. Okay, so what do we know about the before? I'm going to put this page back on here, and as I said, I'm going to turn everything into vectors that we know on the before case. All right, so the first ones that we have are the support reactions, that AX is AX times I. Okay, again, I is the unit vector in the X direction. This guy is pointing positive, so he's AXI. Okay, AY is the AY vector is the magnitude of AY multiplied by J. Again, that's because I assumed that AY was acting up. That's your usual sign convention. And then the moment at A vector is the magnitude MA multiplied by a K unit vector, because this is wrapping in a positive direction around the Z-axis. If you do remember the right-hand rule where I curl it this way, thumb is out, that was the way we define positive Z. So both our right-hand rules are at work here. So that's our moment value. The vectors that we have for P1 and P2, we've handled these before. Okay, so remember what we can do is we can find the X component of 200 newtons and multiply that by an I, and take the Y component and multiply that by a J, and that can split this force that's on an angle into its components. If you don't remember how to do that, go back and look at the components video, the Cartesian components video that we did earlier in the series, and that will kind of explain this process if you're struggling. I'm just taking this force and splitting it into two that I can work with. Okay, again, taking it back to Cartesian coordinates. So when I do that, if we look, here's my 200 newtons. The unit vector, so this is actually the magnitude of P here. Okay, and then I'm going to dot that. That's now the unit vector of P1. Okay, that it's 3/5 I plus 4/5 J. Again, that comes because the horizontal component is 3/5 is the cosine of the angle that is here. And then 4/5 is the sine of the angle. And the X piece gets the cosine, and the sine piece gets you the Y component. All right, and so that becomes the unit vector. So the unit vector on this is 3/5 I plus 4/5 J. And if I do the math, then I end up with 120 I plus 160 J newtons. Gets me that one. P2 is a little bit easier. It's just simply acting in the J direction, but it's a negative J. So P2 gets written as a minus 300 newtons J. Okay, and then the moment at E, okay, which is the moment out here at this point, we said it was clockwise 300 Newton meters. So I'm going to write that as a plus 300 Newton meters K. And I think I said clockwise, it's counterclockwise as indicated by the arrow. Okay, so that's plus 300 Newton meters K. All right, so that's our scenario for that one. Now, if we go look at what we have here, it's exactly the same problem, okay, that we had. So what we know for the after case is that, slide that up a little bit, there we go. that AX is going to be the AX vector, AY vector, and MA vector all the same as what we defined, and that's good because we want them to be the same. Okay, and then we want to find these two unknown values. This is what we're after, and that's the only thing that's showing up on this picture here. Okay, so when I go in and I look, wow, that's really, the glare is horrible again. Okay, I'll bend it over. I think I'm getting a reflection off the white page. Okay, so here's FR taken at A is an unknown vector. That's what we want to find. And then the MR taken at A is an unknown vector. So all we're going to do now is we're going to go through and we're going to play with the before and the afters on this. All right, so first things that we do, just like before, is we're going to find the resultant at A. So we'll put an A on that guy. Okay, and so before we had our resultant vector of the system of forces, okay, on the before diagram. So this is going to be AX plus AY plus P1 plus P2. It's all the forces. Note the moments don't come in because this is a force equation. And then the moments that we have, if we kind of look at, whoops, wrong page. Get this back up here a little bit so we can kind of see what's going on. So this is my before picture that we're going to choose to just arbitrarily take the moment at A. I can take the moment anywhere I want. I chose to do it at A because it will knock out two of these three unknowns when I do that. But all I'm going to do is I'm going to write a moment vector equation for everything on this picture. So we have a position vector from A to A where AX is acting, and from A to A where AY is acting. So that's these first two terms. We know that that's a 0, and we know that that's going to be a 0. Okay, which will knock out those two terms altogether, regardless of their value. Okay, we then get the position vector from A to B crossed into the P2 vector. Okay, and again, this is a vector equation, so everything is being added on here. Okay, and then I have from A to C, I'll pull that down, to C crossed into the P1 vector that we just wrote. Okay, and so that's the equation for this piece here. We also get the support reaction MA, and we also get the moment vector at E on this. So that's the expression for the moments for the before case, when for the moments at A. Okay, now for the after case, okay, we can kind of come in and we can look at it. It's pretty easy that the AX, AY, and MA moments are all the same as they were before. MR is a concentrated moment, and then in this FR guy that we just found that we're looking to find in this, okay, will be the moment at A. We'll have an RAA on that as well. Okay, so we're doing things a little bit out of order. I'm actually writing both equations at the same time. I really only need the R before and the R after. The R after is AX plus AY plus FR at A. Okay, and then just so we have the moment equation, R from A to A crossed into AX plus R from A to A crossed into AY plus R from A to A crossed into FR. So again, that's 0. This is 0, and this guy is 0. Okay, plus the moment at A plus the MR vector taken at A. This is that resultant. This is what we're after, is this guy here. Okay, so all I'm going to do is I'm going to take my afters and my befores and set them equal to each other. So the first one we do is we do the forces. So we're going to do the R before, R after, set them equal, and then solve algebraically. So if I do that, R before to R after, I just basically rewrote everything here. And just like we had in our last case with the single force resultant on here, I end up with the same AX and AY on both sides, meaning they cancel if they're truly equivalent. So the resultant force part of this is just simply going to be P1 plus P2. That will be the resultant force at A on the after diagram. Okay, so if I go through and I work on the math just a little bit on this, my FR at A is now 120I plus 160J. Okay, that was my P1 vector. And then plus P2 is minus 300 newtons J. Then I can do the math, and I know that the J pieces will add together. Okay, so I end up with 120I, okay, minus 140J, because it was plus 160 minus 300, so it's minus 140. So if we look at what that means that resultant vector for the entire system, when I relocated it, will have an X component of 120 in the X, and it will have a minus 140 in the Y. Okay, because again, remember, Y positive is acting up. Y positive is up here, X positive is over here. This guy is acting in the opposite direction because of the minus. All right, now we can have a little bit of fun. Once you have that vector for the resultant, we can figure out what its magnitude is. Okay, and so all I do is do the magnitude of the components of this guy. So it's 120 squared plus a negative 140 squared plus, again, we could be writing, you know, plus 0k here if we wanted to. That's fine. Okay, and so that would be the z term. So that's a three-dimensional value. If this is non-zero, it's the exact same approach. It's just we put in the non-zero value there. All right, and so the mathematics says that that resultant force is 184.4 newtons. Now, I rounded. There's some more decimals on there, but just that's the nature of this kind of problem. Okay, we can also figure out, well, what's the angle of that resultant? So maybe I want to know, instead of, you know, ij's and k's, I want to know what angle this is measured from the x horizontal. So I can take the tangent inverse of the magnitude of 140 over the magnitude of 120. And if I do that, this angle is 49.4 degrees. Now, in the picture, we know that it's being measured what would be in a clockwise direction below the x-axis, but that's the FR vector that's happening for us there. So we've got FR. Perfect. Now we can go in and we can do the math for the rest of it, which will be exactly the same process, except now we do it for the moments. Okay, so same exact game. The moment before taken at A is the same as the moment after taken at A. All right, so here I'm rewriting my entire expression, that the before moment at A is this whole thing. This is the exact same as we saw before. And then the after is the exact same as we saw before. Okay, and so what happens then is if I go through and I set before, and again we're doing equals after, what you notice again is the AX, AY, and MA terms are all common to both. Again, the support reactions have to be the same in before and after. And so this proves it. So basically they will cancel each other out. I don't have to worry about them. And the only things that are left on the before case are RAB crossed into P2 plus RAC crossed into P1. Okay, plus then the ME vector that was that applied thing down at point E. Okay, and all of that is equal to my moment resultant when it's relocated to the A location. All right, so super easy. Okay, so the only thing that I need to know in all of this, because I know the forces and I know ME, okay, and we know that what we're after is the MR, all I need now are two position vectors. I need the position vector from A to B, which if I put this picture back up here so you can see it, the position vector from A to B is going to be a 2i vector because it's on the x-axis, and the position vector from A to C is going to be 2i and 0.75j, positive on both terms. Okay, and so those are the pieces. And as I said, that's what we've written here. 2 meters I plus 0j plus 0k, and 2 meters I plus 0.75 meters j plus 0k. All right, so now I can go through and I can solve this equation. So I'm going to write I got the whole thing. I'm going to do the 3x3 determinants for my cross products. ijk across the top. R goes first, F goes second. So my R, so if we do the first term, RAB crossed into P2 is going to be a 2, 0, 0. That was the RAB. Okay, and then my vector is a 0, minus 300, 0 on the bottom. Okay, and then for the second one, which will be my RAC crossed into P1, that's this guy, ijk on the top. It's 2, 0.750. That was the vector RAC. And then the vector for what would be P1 is plus 120, plus 160, 0. That's what we derived before, and everything is Newton meters. Okay, and then I add in my ME, which was a positive 300 there in the K direction. Okay, and then all of that will be equal to my MR taken at A. This is my after side. My before side is this big thing here. All right, so if we do the math and we do some simplification, there we go. All right, so we have a minus 600 Newton meters K. That's the result of solving this. Okay, plus 230 K. So again, all we're doing is, you notice that I have zeros here. I'm doing a 2 by 2, so 2 times 160 minus 0.75 times 120 times K. That's this term. And if I do that, that number ends up being plus 230. Okay, and then my plus 300 is on this side. And notice everything is a K vector. And for two-dimensional problems, that's what will happen, is our moments will always have the same values. If this was three-dimensional, you might have I stuff, J stuff, K stuff, in which case your vector would be three-dimensional also. All right. So then when I go through and I do my math on this, okay, the MR vector, okay, is going to be a minus 70 Newton meters times the K unit vector, okay? And what that means in this, when I wrote this, because I assumed this was positive, the negative sign tells me that what I drew on the picture is backwards, that MR is actually, so instead of being 70 Newton meters counterclockwise, it's actually a negative 70 Newton meters counterclockwise, or that the magnitude is 70 Newton meters and it's going in a clockwise direction, okay? And that would be the resultant moment. So those two pieces together will give you the picture that we had here, okay? That my FR vector, we said would be, if I write all this down, would be 120I minus 140J, and then my MR vector here is a minus 70 Newton meters times a K direction. And again, this will be a Newton units on that. And that would be your final picture of the equivalent system to what we showed on the very first picture. So we can take a very complex system with lots of things happening, and I can turn it into an equivalent system at any point that I want to do. Again, I just chose A just kind of as an arbitrary example, but there will be times that you're wanting to understand internal behaviors at certain locations, and so we will cut things and take equivalence at the cut. Or maybe I need to know what's happening at a hinge or at another support or at some other critical location that I'm interested in. You know, and this is the exact approach that you do. The whole trick in both of these methods that you've seen in the last two videos is to play with the after diagram on here and set the picture up exactly right. And again, the picture is exactly the same. It's just that you either know the moment or you don't, okay, or you know the location and you don't. You just got to remember those three cases for each picture, and I've showed it to you in both of our videos now, okay? This set of assumptions is the key for both videos. FR is known, location that I'm interested in, coordinates are known, and the moment is unknown. That's all that was special about our equivalent force couples. When you look at the single force resultant in the last video, it was FR known, location unknown, but MR was 0. So you always know 2 out of the 3, and you always know FR because you use the same tactics to find it. It doesn't care about the moments or the position or the location of the point. You just find the resultant of all the forces and then basically pick the force up and you relocate it on those. All right, so that's kind of what we're looking at as far as equivalence goes for force couples. It's a lot of different types of problems, but if you do it as a before and after approach, you should be in good shape. All right, most textbooks don't necessarily write it this way, but I like to do it because I can see everything. And I make sure that I include all the support reactions and everything that I do, as well as my internal forces that are exposed, external forces, and even self-weight all factor into my object, regardless of what the object is, okay? And then I just make sure I get that after picture right and my assumptions, and then you're able to go through and solve it. So I hope that's made sense to you. It's not a hard concept once you kind of do it a couple of times. So if you've got questions, leave me some feedback down below in the comment section. Otherwise, make sure to like and subscribe to this video if you found that it was helpful, and subscribe to the channel, and we'll keep you notified of when more are coming soon. So anyway, I hope you all have a wonderful evening, and we will see you guys next time. Happy engineering.